So if you are as old as I am and you got started in the field of computing, say in the 70s and 80s, you probably heard of Plato. And it was almost this mythical thing that was out there that nobody quite knew what it was. But the thing that you probably knew most about was this, the famous plasma display that they had. It was quite an impressive display. And it really sort of set the stage for the idea that this was a very novel system, something that was different and out of the ordinary. And that's kind of what the reputation of it was for a very long time. And what we're going to do today is really sort of go through the development, the evolution of it. And right toward the end, we're going to take a look at how you would create a lesson. How do you program in the Plato system? And I will mention that there is today an online instance of Plato running that anyone can log into and use. And I'll talk a little bit about where that can be found at the end. Now, there are a number of people I'll be mentioning as we go through things. Here are some of their names. I want to kind of caution that it's not a one-person or just a few-person project. The number of people who were involved with Plato numbers in the hundreds. It involved people over a span of a good 20 to 30 years. But these are a few of the particular ones that I'll be mentioning as we go through. And it all starts with the machine called the Iliac. And here's a picture of the Iliac. Now, I have to tell you that I have a little bit of a fond spot for the Iliac. One of the professors I had as an undergrad, he had done his graduate work at the University of Illinois and had worked on the Iliac way back in the 50s. And so it's always been kind of one of the machines that I've had a little bit of a fond spot for. Now, the Iliac has kind of an interesting history. It turns out that it's a companion to another machine called the Ordvac. Now, Illinois had contracted with the Army to build a machine for the ordnance work. The machine was destined to go to the ballistic proving grounds in Aberdeen, and it was going to, when it arrived there, would have joined machines such as the ENIAC, the relay calculators that were done by Bell Labs during World War II. It arrived very similar time frame to when the EDVAC showed up there. And the Army and the University of Illinois had an arrangement so that when the University of Illinois built this machine, the Army provided enough funding for them to make a second one. And the second one would stay at the university. And so that was Iliac. Ordvac was made for the Army and delivered to Aberdeen, Maryland. Iliac stayed at Illinois and became the beginning of their computer program. Today, of course, we think of it as Iliac 1 because there were a number of other machines built at the university that were follow-ons to this. One of the most famous being Iliac 4, which was a heavily parallel machine done in the 1970s. The architecture of both the Ordvac and the Iliac were not entirely clones, but pretty close to clones of the machine that was being done by von Neumann and his team at the Institute for Advanced Study. It was the machine that von Neumann went to go work on after he had been exposed to the ideas that became the EDVAC project, where he wrote his famous first draft of a report on the EDVAC, and went back to the IAS and started a computer project there. And the architectural ideas that were embodied in that machine fed into a large number of projects, the Ordvac and the Iliac among them. The Iliac was a pretty successful machine. It ran for a good 10 years. It started operation in 1952, and it wasn't retired until 1962. And it's in the later part of that the Plato story starts. Now, Daniel Alpert is the director of the ILLIAC lab, and he is approached by another faculty member at Illinois by the name of Chalmers Sherwin. Now, Sherwin has studied people like B.F. Skinner and people like Seymour Papert at MIT, who have been investigating, kind of studying the concept of learning and trying to figure out, can we scientifically improve the educational process? And Sherwin is basically thinking, we've got this computer here, surely a computer can be useful in helping out the process of education. And so he approaches Alpert and William Everett, who is the Dean of Engineering, and says, hey, here's some ideas that I have. And it gets the university, particularly in the roles of Alpert and Everett, very interested and excited in the idea of building some kind of a system for experimenting with educational techniques using the ILLIAC. However, Sherwin isn't the person that is interested in administrating and running such a project. So in time, primarily Alpert recruits another newly minted PhD from Illinois by the name of Don Bitzer. And Bitzer is a consummate engineer. He is the sort of person who has no time for budgets and processes and procedures and even documentation. Any time that is not spent creating and building is time wasted. So as things develop, eventually reports, of course, are written. Most of them are actually written by Alpert, and he's always listing Bitzer as a co-author on them. But Bitzer is kind of the technical lead in all this. So they begin to prototype an idea in 1960. And the concept is basically, so let's kind of create a sort of interactive textbook. We're going to use good old-fashioned 35mm slides for our presentation of most of our material. And what we want to do is we want to control what slide gets projected by code running on the ILLIAC. Now, it also has the ability to generate a little bit of output on its own. And so what happens is you've got the slide projector output being captured by a camera, and then that's combined with the information that the computer can generate and overlaid on what amounts to a television screen that the student sees. If you've watched the demonstration that's known as the mother of all demos by Engelbart, you'll see some of the same sort of idea of having both plain video and computer-generated information overlaid in the same display. So the idea was you would present information to a student. They would have a keypad, a box with about 15 or 20 keys that lets them answer questions, indicate whether or not they are ready to move on to the next segment, and so on. And that would then be the input to the code that was running on the ILLIAC that would control what's happening in which slides were being displayed. And the basic architecture looks like this. You've got this keypad of some sort. It's not a full keyboard yet, but it's as I said, a box of something like 15 to 20 keys that the student can use to interact with the system. That becomes the input to the ILLIAC, and then it turns around and generates some output and primarily is controlling these slides. And the view is just an ordinary television. So this becomes the basic model on which the system is built. Now, as you might guess, one student using a computer of the scale and expense of the ILLIAC isn't going to be very impressive. And so the next stage is we want to be able to support multiple students. And so this kind of evolves into what we might think of as Plato II. As you might guess, early on, these things are happening kind of fast. So where Plato I starts operating and they're able to demonstrate it in 1960, we've got something happening in 61 for Plato II. But it's still the same basic idea. We have the ILLIAC controlling slide projector. We can have a couple of students now operating from this. And so you end up having to then take input from these two different key boxes and select which one is going to be the input. You have to have the ILLIAC controlling which one is going to be the output, or which one am I going to be changing output to at this point. Now, the input, of course, is relatively slow data rate, so that's no big deal. We can use ordinary phone line type connections for this. But how are we going to distribute the video? Now, in a one-person test bed, that's easy enough. Now we want to somehow distribute it to multiple users. Well, being driven primarily by the engineering of things, they looked for what was the simplest and cheapest solution. And it turns out that the University of Illinois had a television station, call letters WILL. And what they did was they weren't broadcasting all day long. So the Plato team arranged with the television station to use a couple of hours that they weren't normally broadcasting. And so they generated their video feed from their laboratories over to the television station. And so anyone who tuned into the WILL television station during that window every day when the Plato team was working would see whatever the Plato system was broadcasting. And so you could sort of watch what the testbed students were using or doing as their experiments. And the structure of it, as you can see, was still pretty much the same as it had been. But now we've got this switching mechanism that has to decide, well, which display am I updating? Because in principle, what you really want is for each student to see a different display. Now, in the television broadcast kind of form, there was a limit to what you could do there. But the basic idea was we want to have each student effectively watching their own program of this. So, you know, we're making some progress. We're prototyping things. And now it's time to start getting serious. We need a new computer to do this. ILLIAC is ready for retirement. You know, the new impressive computers are transistorized. We don't need vacuum tubes anymore. You know, it's time to really start doing something a little bit more serious. And so we go and we get this computer. This is a Control Data 1604. Control Data Corporation has expressed some interest in this project. They've got an impressive machine that the project would like to get. And so they go and seek out the budgeting for this. Now, the machine itself, if you've not heard of him, you do need to know about Seymour Cray. He was kind of the person when it came to designing high-performance computers for a very long time. The 1604 was one designed by him and his team at Control Data. It used a 48-bit word, so there were 6 bytes, as we would currently call them today, per word. 32 kilowords of memory. So that would be more or less the equivalent of about 180 kilobytes of memory. Now, when they initially sort of said, okay, we want to buy this computer, but for, you know, proper purposes of doing things, we have to get bids. And the CDC bid comes in a little under $1 million. IBM comes in with a bid for one of their 7000 series machines, probably the 7090. And they're coming in at almost $2 million. And so, great, you know, the one we want has the lower price, we're all set to go. And kind of word gets out, and IBM comes back and comes up with a newer deal that comes in a little under the CDC deal. And CDC is still saying, hey, this is how much it's going to cost. The Plato project is still wanting the CDC machine. IBM gets upset, starts, you know, running around trying to appeal to administrators and state government and so on. And nobody wants to tell the project, you have to do this. So they go and have one more round of bidding. And at this point, IBM is coming in with a bid of only $200,000. And the Plato project's attitude is kind of, look, if you're going to play games with us like that, we're not really interested in working with you. And so they did end up getting the CDC machine. And that began a long-term relationship between this project and the Control Data Corporation. Now, on the CDC 1604, they developed the third version of this. Now, the model is still based on this idea of a slide projector. And what they have done is, and this is related to what happened in the version 2 of it. I'm going to go back to that slide for a moment. You'll notice that we've got these two storage devices that are here. Well, what they did in Plato 3 was they used not only the computer-generated material in the storage device, but also the slides were sent to the storage devices. And the basic idea was that this was like a storage screen CRT. And a camera was pointed at it. And that camera was what the student saw. And then you could feed onto this screen whatever you wanted, and it would kind of be frozen there. And so you could give each student different slides. And then that was controlled, of course, by the 1604. At this point now, of course, we're setting up a whole lab of students. I believe the Plato 3 system could support up to 20 such terminals. And so you had video distribution wired into the classroom they were testing this with. And so each terminal was connected to this, what amounted to a cable TV type system. Now, one of the interesting things that happened here was a lot of very young students got involved with this. There was a whole group of high school students local to the Urbana-Champaign area who began working with this system. Some of them graduated, went off to college, but would come back and spend their summers working on Plato. One of the students basically coded up the kernel of what amounts to a little real-time operating system on the 1604 to do the time sharing, and it produced extremely fast response times, so that when a student at one of these terminals hit a key on the keypad, that you would get a response that was very rapid, something that most other systems couldn't quite handle at the time. There's a story about how some of the senior administrator and research folks at the university weren't too happy about having this collection of kids running the system, and they sort of required the students to give a presentation to defend all their design decisions and the work they were doing. And apparently the demonstration was so impressive that nobody ever questioned it after that. And this really was the starting point for a lot of people who later went on to do some pretty impressive work in the field of computing. A lot of people got their start on the Plato system. Now, at this point, of course, we kind of have a system that's working, but we're tied still to that old idea of, I've got to produce slides for everything that I want to present. And computers are substantially more powerful now. What we'd really like to be able to do is generate the imagery that we see on the fly. Of course, how are we going to do that? Well, the first thing we need is a more powerful computer. And so now we get to this machine. This is actually a picture of a CDC 6600. Now, its younger brother, the 6400, is what was used by the Plato team. This was the big machine of the day, okay? Also designed by Cray. The 65 and 6600 members of the line had multiple CPUs. It had a very clever scheme for handling I/O through the what were called peripheral processing units, PPUs. It operated on a 60-bit word. We usually think of these as the early supercomputers. And the Plato team got one of these. And that became the test bed on which they developed Plato IV. And Plato IV is where these plasma terminals came into the picture. You have now full keyboards. The computer is now going to have the student interacting in a way that's very recognizable to us today. We've done away with the slide projectors now. The CDC 6000 series machine is going to be generating the imagery. And we're going to display it on these plasma displays. I mean, at this point, the idea of high-density graphics is a pretty novel thing. The displays, as we will see, were 512 by 512. To give you a little sense of context there, the broadcast television standard operating in the United States, known as NTSC, it operated with a 525 line scan. So what they were doing with this 512 by 512 image is they were essentially saying every scan line on the television could be individually addressed. And compared to the quality that you would be able to see with broadcast television, this was absolutely mind-blowing. The amount of detail and the resolution was like something nobody had ever really seen before. Now, the interesting thing, and this is where the double E in me just wants to totally geek out, but I'll avoid going too far into it. Because they had this video network already set up for distributing information, and they were no longer distributing imagery from slides and other things cameras had caught, they needed now to transmit digital data. And so what they did was they actually took the digital data, encoded it, and modulated it into television video signals and sent it out over the same video cabling. And then the terminals would demodulate it and look at the bit pattern and say, oh, this is a sequence of bytes addressed to me, and I'll take this as a command to draw a line or write a letter on the screen or something like that. And that's actually how they distributed the information to everything. You got to remember, this was before Ethernet. So this is how you could take a machine like a 6600 and distribute in high speed the commands out to these terminals to get them to draw lines and put text on the screen. And this is the architectural diagram. I'm not going to get into all the details of it, but I'll just kind of highlight a couple of pieces. So up in the upper right-hand corner of this figure is the CDC 6000 computer. This is what's doing all of the heavy lifting. It's generating all of the lessons. It's taking the information from the students, and it's looking at their answers and saying, okay, is this answer right? Is this answer wrong? What kind of feedback do I need to give? And these smaller lines you see coming along the bottom, up the left, and into this little box right here. This is the keyboard information, the essentially low-speed information over ordinary phone lines. And then there's this input concentrator, which becomes now an input channel that the CDC machine reads from. Now it generates its output, and they've got this custom bit of circuitry here that generates the video signal based on the digital data that is being transmitted out to the various terminals. And then that goes through standard television equipment. That goes out over the cabling, and then each classroom has a distributor that receives the video coming in. It looks at the addressing information to see if it's destined for this classroom. And if it is, then it demodulates, well, it demodulates it to figure that out. But once it recognizes this is for this classroom, it then distributes it out to the individual terminals in the classroom. And so by doing this, you could have a large number of classrooms scattered across a fairly large area campus and be able to support them all through this one machine. And there was even the capacity now to start having remote instances of this. And so you could have these occasional one-off terminals that would go out somewhere. Now the terminals themselves, of course, like I said, are these interesting plasma things. And here's one of the early prototypes of the plasma work. Now, the primary engineer who was doing most of the work is named Robert Wilson, but there was another physicist who really consulted and had a lot of input on the techniques that were used, named Gene Scotto, or Scotto, I'm not sure how you pronounce it. And what they realized was they could basically create a plasma by having a high-frequency alternating field across this gas. They were using neon gas, and rather than trying to excite it directly with electrodes directly touching the gas, what they did was they had the electrodes on the outside of the glass, and it created a field using a capacitive effect. And so you generated a high frequency, high voltage signal across a place where a vertical line and a horizontal line crossed. So you had all the vertical lines on one piece of glass, all the vertical horizontal lines on the other piece of glass, and where they crossed, you had a dot. And what we see in this picture is a 16 pixel by 16 pixel prototype that they built. And each one of the dots there is one crossing point of and I believe in this picture, the horizontal lines are on the front piece of glass and the vertical lines are in back. By kind of developing this proof of concept in-house, they were able to say, okay, we know this will work. So we're going to ramp it up to 512 by 512. We'll have this manufactured commercially by people who really know how to do these kind of display systems. And you have to remember, this is now what becomes later our modern plasma flat screen TVs, which largely have been supplanted by CRT-based ones. But for a fairly significant period of time, if you wanted a big screen, flat screen TV, it was plasma-based, and it was based on these ideas that were done here. And when we get to a 512 by 512 resolution, we get to see something that looks like this. And we have this really impressive kind of resolution here. Now you got to remember, this is early 1970s. And we're talking about a time when most of us, if we were using a computer, it was using a teletype. If we had video at all, it was a character-based screen that was maybe something like 80 characters wide by 24 lines. In the kind of lower end computing world, even getting that much resolution in your screen was a fairly advanced thing. especially if you wanted lowercase. That was a big deal. Uppercase 12 lines by 60 characters was pretty typical. But to have this kind of resolution and be able to do graphics with it, that was something else. And that's kind of why those of us who grew up in the field in the 70s and 80s, Plato was this kind of thing out there we had heard of and that had these amazing capabilities. But, nobody ever got to touch one because it was largely this relatively confined thing in the world of the University of Illinois. Here's another good example of it, showing basically, as you can tell from the picture, how the eye works. And you have a number of different pieces of this that are labeled, and those labels are used in the various lessons that are essentially teaching a medical student about the different parts of the eye, how it works, and what the medical student needs to know about the eye in terms of diagnosis and treatment. So the question then becomes, how do you go about programming these lessons? Now, early on, you wrote Fortran code. And of course, people built up useful libraries of things that would do handy things like drawing pictures and so on. And there were a couple of attempts at trying to script these sorts of things. And it turns out that during a particular attempt at a training session, there was going to be this, okay, people who want to create lessons for this thing, we're going to teach you about how to program these lessons, how to construct the figures and how to make it ask questions and check the answers. And a particular young programmer on the project, Paul Tenzer, he was kind of toying around with building up some examples for this class. And he began thinking, well, instead of just having a whole bunch of Fortran code that's just a bunch of call statements, what if I just, make these different functions their own commands? And I can just generate the code directly from that. And as he begins playing around with this, he creates this language called tutor. And here's an example of some tutor code. And this is a fairly simple one that just generates a simple geometric figure and asks the user, well, what kind of a figure is this? Now, I'm going to kind of go through this, not in a huge amount of detail, but I want to give you a little sense of what is happening here. The first line, which is defining a unit, unit geometry, that's essentially defining the name of conceptually a lesson, but you really want to think of it as being the name of a subroutine, a function, because you can call these from other units. Now, the at command that's on the second line, that's just saying, where am I going to put something on the screen? Now, there were a couple of different methods of describing it. If you used this 4-digit number type of approach, what it boiled down to was row and column character positions. If you wanted a higher resolution, you could do that a little bit later. Initially, it was just here in terms of the row column. So it's specifying that at 1812, we're going to write the text, what is this figure? And then we have this draw command, which is going to draw some lines. And you might be able to sort of tell that this is a closed figure starting at position 510 and ending at 510, and has 2 other points. So as you might guess, this is drawing a triangle. And we'll see what the screen looks like in just a moment. The thing that really kind of made this, sort of proved to Tenzer that this was a technique that was really going to work well, was being able to say, okay, now I can say, here's where the student puts in their response, and I can now evaluate it. And that's what that arrow command is doing. That specifies the position on the screen where it draws an arrow on the screen. That is where the user, the student, types in their input. And you can specify right answers and wrong answers and what kind of feedback to give in these cases. So in this case, the keyword answer is used to specify what happens, what a right answer consists of. And in this case, we're specifying that the words it, is, and a are all optional. We'll ignore them. It's perfectly okay for the user to put them or leave them out. It doesn't really matter. The right and RT that we have in parentheses, we're going to insist that one of those be there, but we're going to treat them kind of as synonyms. And then the word triangle has to be there. And so the right message that follows that answer is how we respond to the student to tell them they're correct. On the other hand, if the student responds with the optional it, is, or a, followed by the word square, then we're going to write out the message, count the sides. And that's essentially how you constructed one of these scripts. You would present something on the screen, you would have some kind of question, and then you would do something to process the student's answer in terms of patterns that would be recognized as a correct answer or an incorrect answer. And then typically you'd have some kind of a catch-all for if it was a wrong answer and you didn't recognize it as a specific wrong answer, you'd give some kind of more general feedback. And what this would do when it was displayed would look something like this. And here's a case where the student who has viewed this has answered a square. So we have the triangle drawn on the screen. We have the question, what is this figure? The student has answered a square. And the system, because a square has been identified as a wrong answer, gives us the answer no, and then the message count the sides. And so this kind of gives you an idea of how you would create these tutorials. Now, of course, being Computer Science Education Week, we look at such a language and we say, okay, but I got to be able to loop. I've got to be able to have conditionals. I need to be able to actually write programs that do more interesting things. So I'm going to show you another example, a somewhat more complicated one. This also illustrates things like how we can deal with variables, how we deal with higher densities of things. We even have comments in this. This first screen worth is really just kind of setting up the what we're doing. The interesting thing is that after the unit here, we also have next and back keywords. These would define the flow of a set of screens in a lesson. And you could use that information to allow the student to back up, to review something, to say, okay, I understand this, I'm going to move on to the next screen, that sort of thing. Now, where this gets interesting is on the next page. So here we have some more advanced types of things. We're asking here in this first write statement, we're asking the user to type a function of the variable x. Now, the interesting thing here is the user can type any function that is recognized as part of the language. And what happens is we read that into a variable called string. That's what the store a command is doing. The second parameter to store a is the number of characters to store into the variable string. JCount is a built-in variable that tells you how many characters were in the answer that the user typed. The J comes from the term judge. Throughout the tutor system, the idea of evaluating students' answer was referred to as judging the answer. The OK keyword just said, We're going to accept whatever answer the user gives us. And now we're going to start doing some stuff. The calc keyword essentially evaluates an expression. One of the things that's really interesting about this is notice that the assignment operator they have here is not an equal sign, it's a left pointing arrow. They had no compunction or no, that's what I'm looking for, no aversion to defining new characters and using things that were outside of the usual character sets. And so they used a left pointing arrow for assignment, the thing that we wish we could use, but ASCII didn't give it to us in the character set. Now, here things get kind of interesting. The compute command computes it essentially evaluates a function expressed in the form of a string. So we take the string the user has given us and we go and evaluate it. Now, compute has the byproduct of compiling this into machine code. And the last parameter to the compute, the variable called point, this identifies the location in memory where the machine code is for what we've compiled out of the function that the user gave us. We get a result based on the value x, and that's going to be the initial point in the graph. So the compute statement is very broad, very general. Essentially, it lets you take user input and make that become code that you're going to be using. The go-to statement, remember, this is before Dijkstra writes his famous go-to consider harmful. So go-to was a perfectly reasonable thing at the time. It is like the Fortran go-to. Now, if you're familiar with old Fortran, go back to Fortran 2 days, there was this thing called the computed go-to. And effectively, you would evaluate an expression, and then you have a sequence of statement numbers that for different values of the expression, it would take you to a different statement number. They had the same sort of idea here. Now, basically what it boiled down to was anything that was negative would be the first option. And then starting at 0 and consecutive integer values after that, you could specify whatever different set of destinations you wanted. Form OK was a built-in value that would tell you whether or not there had been an error in the previous computation. If there had not been an error, it produced a negative value as a result. And the X option as the place to go on the negative value meant do nothing. Otherwise, it went to a separate screen called bad form. So this is just the error check that says if the function that the student gave me was bad and I couldn't evaluate the function at x equals 0, then I'm going to give them some kind of feedback. Otherwise, we move on. GAT, that's just like a graphical version of the at that lets you go to a more fine-grained location. And now we have the keyword due to. And again, you can kind of see the Fortran influence here. This is basically like a Fortran do statement. You specify where you're going to end the loop. And this is just now a word that you create, goes in as a command. And then we're providing a range for the variable x. In this case, from 0.1 to 10 in 1/10 increments. And within that loop, we're going to do a new instance of compute, where we're going to once again evaluate the function. This time, since we've already compiled it, and we're providing this point variable that tells us where the machine code is, we just rerun the machine code. Once again, we do an error check, and then draw the result. So the net effect of this program is you essentially get a grid or a set of axes on the screen. The user is told type in a function, and it draws out that function for the student. And here is an example of that being done. You can see at the bottom of the screen, is the function the user typed in, 2.5 sine x over 1 plus x cosine 2x squared. And evaluated on 10th increments of a tenth in the variable x, you get this function printed out here. So this kind of gives you a little sense of what this language was like. It wasn't exactly what we would think of today as a particularly convenient or nice programming language. When the Plato people and the Xerox PARC people kind of exchanged ideas, as you might guess, people like Alan Kay at Xerox PARC, who was creating Smalltalk around this time, didn't think very highly of this language, but it was general enough that they could do a tremendous amount with it. And in fact, one of the things that people most remember the Plato system for today were things like the games that were on it. And they were all written using Tutor. Entire kind of conversational environments that developed into the sort of social environments that we think of as so common today. A lot of those got prototyped on Plato. There's a whole kind of another side of its history in how it influenced the social aspect of computing that those of us who are old timers kind of think of today as eternal September. That whole thing all has its roots in Plato. And if you're interested in trying it out and playing around with the Plato system, there's a website called cyber1.org, C-Y-B-E-R, the digit 1.org. And that is a sort of portal that lets you download a terminal emulator of the Plato terminal system that will then communicate with their simulation that is running on CDC cyber hardware and running the Plato code. I believe they grabbed a version that was sort of 80s vintage, and you can actually set up your own account there and participate in the community there, just like all of the people did back in the day. So that kind of gives you a quick picture of how the Plato system came to be, how people were able to write programs in it for either teaching purposes or also games and other such things. So at this point, we're getting close to using up our hour. So I want to open the floor to any questions that anyone has.
If you have questions, feel free to shout them out or write them in the chat, and I'll be happy to say it for you.
Name's Chad Piper here. Firstly, thank you so much for this awesome presentation. I am an alumni of Illinois, and I dedicated my dissertation to Michael Feynman, who was the graduate director at the time. And, like all great teachers, he was a physicist before he was a computer scientist, and he worked on ILLIAC 2. And I'm just wondering, how did it go from ILLIAC 2 to Plato? Like, what was was it always an educational motivation? I'm just wondering how it went from ILLIAC 2 to Plato, because I know that in some of my research for my dissertation, the physics department still based some of their pre-assessments and post-assessments in their classrooms that I did a kind of a pilot study on based on that model. But I never really understood the transition from ILLIAC 2. Maybe I missed it. And you said it, ILLIAC 2 to Plato. Was it always an educational kind of concept? That's the question. Thanks so much again for this awesome talk.
Thanks. So to try to fill in what I know of it, I certainly don't claim to be an expert on the history either at Illinois or Plato, but the way I understand it is that the sort of the line of iliac computers, starting with the iliac 1 and as I say, kind of culminating with iliac 4, that the research that went into that was its own area, but looking at different applications of it was kind of an open thing to anybody in the university. For example, remember I mentioned that the first iliac went into operation in 1952. So if you fast forward to 1957, when Sputnik launches, one of the first things they do is they hop on the machine and feed in information to try to calculate the orbit of this new satellite. And the idea of using the computer for teaching purposes is brought in as one of the kind of suggestions of, hey, here's something we can use this computer for. And it really did kind of spawn its own project that then justified purchasing and getting grants for other equipment outside of the iliac series. So yeah, it started out on the first iliac, and then it moved over fairly quickly to the CDC series of machines. I saw a question pop up about whether or not it is still in use and still sort of available. Eventually, as the project matured, CDC actually took it on as a product and attempted to really kind of make a business out of this. And they did some success in that. But I think it was kind of one of those things that by the time they were really in a position to push it, it was now finding itself competing with the likes of AOL and the other sort of online forums and that kind of thing. And I don't know that CDC really knew how to play in that space and compete in that sort of thing. And so it ended up kind of fizzling in time. As I understand it, I think most of the code of the system has been largely recovered and is something that is available online and people can experiment and play with. And as I said, cyber1.org does have a running system that you can connect into. And I think there's a number of people who were part of the original community who still occasionally hang out on there. Do we have any other questions? All right, well, I think we have used our hour almost exactly. So I'd like to thank you all for coming out today. I hope you found it interesting. Those of us who are still here at Drexel and working on finals week, good luck to you all and on the grading as it's coming up. I will be disappearing into grading very soon myself. So thanks again.